So welcome everybody to this Bamboo webinar within the framework of the European Green Week. So we will have a two session webinar. During the morning session, we will see the technologies to achieve the zero pollution industry. Within the afternoon session, we will see how those technologies are being applied in different industrial sessions. So first of all, I want to warn you that this webinar are being recorded, and so afterwards will be shared within the YouTube account of Bamboo Project for you to be checked afterwards. So first of all, my name is Aleida Lozale. I am the project manager of Bamboo Project. And now I give the floor to my colleague, Cristina Gonzalo, who is Bamboo Project Coordinator, and she will explain you an overview of Bamboo Project. Okay, so this is your turn, Cristina.
So hello, good morning, everybody. Let me share my screen with my presentation.
Okay, we can see it.
Perfect, thank you. So welcome again to this Bamboo project towards zero emissions energy intensive industry partner event in the framework of the European Green Week 2021. As Aleida said before, I'm Cristina Gonzalo. I work at CIRCE Foundation in Spain, and I'm the project coordinator of Bamboo Project. So first of all, let me introduce you a little bit some basic data about the project. This is a project funded by the European Commission by means of a SPAR 2018 call. So this project started in 2018, and it started 2.5 years ago, and it has an overall duration of 4 years. CIRCE is the project coordinator, and as you can see, we count with a very strong consortium with 19 partners, including universities, research centers, small and medium-sized enterprises, and of course industrial partners, because this is an innovation action, and this means that we are demonstrating different technologies in a relevant industrial environment. And we work with companies from the steel sector, such as ArcelorMittal and Sidenor, also from the petrochemical sector with Tupras, pulp and paper sector with UPM, and finally also with mineral sector with Grecian Magnesites and Magna. So what is the motivation of the project? As you know, the energy transition towards a secure, competitive and decarbonized energy system is a challenge for the European Union, and also, of course, for the European resource and energy intensive industries. This is because they must adapt their current consumption and production patterns to a higher share of fluctuating renewable energy supply, and also because we expect that in the following years we will have higher and higher restrictions regarding emissions. So in this context, new technologies are required to enable a higher flexibility on electricity supply, while at the same time decreasing the consumption and dependence of fossil fuels. So In this sense, Bamboo project is aimed at demonstrating different innovative technologies for waste heat recovery, electrical flexibility, and waste streams valorization. And we are working in 4 energy and resource intensive industries, including the steel, the petrochemical, the pulp and paper, and the mineral sectors. So how does Bamboo project contribute to the decarbonization? So we are working in 3 innovation pillars: waste heat recovery, electrical flexibility, and waste streams valorization. And the first one, waste heat recovery, includes the demonstration of different technologies to valorize waste streams because they have a certain temperature, so that we can valorize them and use where they are required in other parts of the process. Second innovation pillar is electrical flexibility, to offer the industries the possibility of taking advantage from lower electricity price and potentially provide grid services, as well as enable the integration of renewable energies in the grid. And the third one is waste streams valorization. We work on different technologies and processes for the valorization of on upgrading of different technologies that will allow us to valorize waste streams that have a certain calorific value, and then they can be used as fuels in other processes in the plant. So now going to the first innovation pillar, as I commented before, waste heat recovery, we work on the demonstration of 2 technologies, high temperature heat pumps and organic Rankine cycles. In the first one, high temperature heat pumps, we will demonstrate their use in the steel sector in order to upgrade low to medium grade waste heat to produce a stream with higher temperatures. The particular application here is the valorization of waste heat from an acid regeneration plant that will be introduced to a heat pump for steam generation, and to use this steam for the acid bath heating. And we will test this application in ArcelorMittal from the steel sector. The second technology is organic Rankine cycle that we will demonstrate at the petrochemical sector. And the aim here is to valorize medium grade waste heat to produce electricity. We will work on the valorization of waste heat from a crude distillation unit to produce electricity by means of organic Rankine cycles. So this is going to be to have a direct impact on the electricity bill of the company of Tupras, which is our demonstrator from the petrochemical sector. Second pillar of Bamboo project is electrical flexibility. In this case, we are working with the pulp and paper sector in the demonstration of strategies and technologies to increase the energy flexibility of the plant. In this case, the paper plant will operate as a battery in the regional power grid. This approach means that during summer, the idea is that when a higher production of photovoltaics is expected to be produced in the region and to be integrated in the local power grid, the idea here is to reduce or shut down the own power generation of UPM's plant, so that they can consume this surplus energy from the power grid. Whereas in winter, where low or missing renewable generation in the grid is expected, UPM's own generation will be operated to produce energy not only for internal use but also to supply this extra power to the local power grid. So in this case, these energy flexibility strategies are going to make possible or to facilitate the integration of renewable energies in the grid. And the third innovation pillar, as I commented before, is waste streams valorization for their use as fuels in the different demonstrators. First of all, we are going to valorize process gas that is produced in the steel sector to use this process gas as fuel, and this is going to have a direct impact on the fossil fuel consumption because we are going to reduce the fossil fuel dependence and the associated emissions of the plant. In this case, we are working with ArcelorMittal, as I commented before, to increase this use of processed gas in the plant by means of two technologies. First of all, we are using computational fluid dynamic simulations to evaluate the behavior of the combustion equipment when these alternative fuels are introduced. And secondly, we are working on the development of a flame monitoring system that will help to the monitoring of combustion when these alternative fuels are introduced in the combustion equipment, and is going to have a direct impact on the improvement of efficiency and emissions. And also in these innovation pillars, we work with the mineral sector with Grecian magnesites to replace coke by biomass. So again, this is going to have a direct impact on the fossil fuel consumption, a reduction on this fossil fuel dependence. We develop activities, CFD simulations, to analyze the behavior of the combustion equipment when these alternative fuels are introduced in GM's kiln, and also a novel multi-fuel low NOx burner is developed in the project and demonstrated at Grecian magnesites. This not only will allow to reduce the CO2 emissions, but also is devoted to reduce nitrogen oxides emissions. So this is more or less an overview of the different technologies and the different demonstration activities developed in the project. So today we have two sessions for subscribers to further know what we are developing in the project. In the morning session, our expert speakers from the Austrian Institute of Technology, Turboden, Technical University of Braunschweig, Certh and Circe will explain how this technology works and how these technologies can contribute to the decarbonization of the energy and resource intensive industries. And during the afternoon, we have a second section where our partners or our industrial partners will explain their experiences and the successful cases that are being developed in this project. So thank you very much for your attention. I hope that you find these workshops interesting, and maybe yeah, we can move to the next presentation, where Franz Hemminger from the Austrian Institute of Technology will explain more about these high temperature heat pumps that I briefly explained during my presentation. Thank you very much.
Yeah, good morning, Christina. Good morning, everybody. Thank you very much for the introduction. So I will share my screen now. Sorry, the wrong one. Do you see my screen?
Yes, thank you, Franz.
Thank you very much. Again, good morning. My name is Franz Helminger. I'm working for the AIT, Austrian Institute of Technology in Vienna, and I will talk about the waste heat recovery. That means reduce energy consumption and emissions with heat pumps, so-called high temperature heat pumps or industrial heat pumps. To give you an overview of my speech, so first of all, I will tell you our motivation, so why we are doing what we are doing. I will talk about the challenges we are facing with ongoing developments and demonstrations and trainings. And at the end, I want to give you an insight of the impact of the estimation of an impact on European Union level and an outlook for the world market for industrial and high temperature heat pumps. Just to introduce the AIT. So AIT is the largest RTO in Austria. We have around 1,400 employees. And in the subdivision, so in the business unit of Sustainable Thermal Energy Systems, where I am working, we have around 60 colleagues. The AIT is owned mainly by nearly by 50% of the Federation of the Austrian Industry and a little bit more than 50% of the Republic of Austria. You can see here the shares. Coming to the motivation, as I said previously, if you look at the data of industrial heat supply, you can see that a lot of heat is given to the ambient on relatively low temperature relative to the processes where it was used. And this heat can then not be used anymore for the industrial processes. What you can see on this slide is data from 2012 from a study from some years ago. And what we are doing is we are using this low temperature heat, bring it to a so-called high temperature heat pump or industrial heat pump, use a little bit of electricity, lift the temperature of the low temperature heat to a temperature where it can be used again in the industrial process. So that's the general principle, and it's somehow a circular energy use. What you can do with it is you can save CO2 emissions, you can save primary energy, and at the end you can save money. The challenges we are facing are divided in two different main areas. So the ongoing development of industrial heat pumps and the demonstration and trainings of it, coming again to the principle of a so-called compression heat pump. So there are different names: industrial heat pump or compression heat pump or high temperature heat pump. It's always the same. On the left-hand side, you can see there is the low temperature waste heat, which is given to a working fluid. It's also called refrigerant. This working fluid is then evaporated and compressed in a compressor with using this electrical energy, brought to a high temperature and high pressure, where the heat is then given to the process heat and can be used again. And this is a so-called closed circuit, as the refrigerant and the working fluid is then brought back to the evaporation process. That's the principle of a so-called closed circuit, what we are working on since some years. The other challenge is for our future process heat supply, we have different requirements. So the process heat supply in the future will be more efficient, is needed to be more efficient also to European regulations. We have to decarbonize the process heat supplies, as this decarbonization comes then mainly with electrification. I will come back to this point again with statements from some studies. We are facing there three main thematic areas. So we have to identify the sectors and processes where such high temperature heat pumps can be used in the industrial environment. The technology, the heat pump technology itself, need to be developed and integrated and demonstrated in the processes to get more know-how and to get more trust in it. And we have the third main area is the lack of knowledge and experience at the industrial users and planners. So what can you do with an industrial heat pump in your process? Going to the first main thematic area, just to give you an overview. On the left-hand side, you can see a list of processes where you can get waste heat out of the process before it's given to the ambient. And on the right-hand side, you can see a list of processes where these processes where the heat can be used on high temperature level. At the end, different studies done by different institutes come in principle to nearly the same conclusions. That means in energy-intensive sectors, waste heat in exhaust gases or hot water is used. That's what's on the left side. On the right side is the processes, is a list of the processes, I said, up to around 160 degrees C, including steam for the processes. And you see a lot of processes in the list from the pulp and paper sector, from the chemistry sector, food and refineries, but also smaller shares in textiles sector and also steel making. The next slides show you what is developed already and in development for steam generation and drying processes, as these two use cases are now developed most. And yeah, where we have a most of experience and know-how. First of all, the steam generation. So why heat pumps for steam generation in general? This is why steam is one of the most important energy carriers in the industry. It can be used, or it is used, for heat transfer as well as process reactant. And you have mainly also existing steam networks where you can integrate high temperature heat pumps where you have a high multiplication potential. That's for steam generation. For drying processes in general, why heat pumps in drying processes. If you go to the data and look at the data, then you see that 25% of the final energy consumption in industrialized countries is used for industrial drying. And they are mainly without heat recovery. So that's the main motivation and the challenges. Coming to the challenge of the technology development, the second thematic area, and the integration into a built industrial environment. On this slide, on the left-hand side, you can see a graph, a scheme for a direct steam generation heat pump. That means, if you can see my mouse, on the right-hand side of the graph, you see the evaporator I talked about. The working meter is then brought to a compressor, in that case a piston compressor, and then the hot meter is brought to a steam generator where the working fluid is used to evaporate the water for up to around 150 degrees C, and this steam is then brought back to the industrial process, what is shown here in the center of the graph. There is also another way of generating steam with heat pumps, so you can use a so-called water-to-water heat pump and bring it to a flashbank, and these two different ways of steam generation with heat pumps are now going to be visible on the European market, on the overall European Union, with different advantages and disadvantages. In both cases, you have a so-called closed loop heat pump. Coming to the drying processes to show you what was done in previous years in the drying process. Again, the graphs on the upper left graph, you see again a closed loop heat pump for drying with air as drying agent. On the lower left graph, you see a so-called open loop heat pump for drying with superheated steam. So this closed loop I already explained for the steam generation is nearly the same. On the left-hand side, the only difference is on the left-hand side, you can see here a condenser where the heat is given to a heat transfer media, where then the air, the drying agent air, is then heated. And on the open loop case, you use directly steam as working fluid, and no lubrication is allowed there, and is a little bit different technology. I'm showing this to you as in the project Dryefficiency, which is dealing with the efficiency of drying processes up to 160 degrees C. These two technologies are used, and in parallel we see that development of the market for closed loop heat pumps are now up to around 120 to 130 degrees C of supply temperature. So there's still a difference from the scientific and research point of view to the market, but we see a very strong development from the on the market with high temperature heat pumps. Coming to the third challenge, the lack of knowledge. So we are addressing the humans behind in the industry and also of the users. So we are talking about industrial users. We talk about how to sail it. We are talking about the integration in terms of industrial processes, in terms of planning, manufacturing, and operating. And to address this lack of knowledge in different projects, we see different training opportunities. As these industrial heat pumps are now known a little, not known that much up to now, but the interest is very high. So we have ongoing training programs in the Dryefficiency project, but this project will end this year. And we are working on offers in the Bamboo project to offer trainings. This will start roughly at the end of this year, and there we will address all groups of stakeholders. Coming now to the next point of my agenda, which is the estimation on European level, so the impact on the EU, and also, I want to talk about an outlook for the world market in the future. The heat pumps are very promising technology for our future energy systems. So I will show you some aspects from different sources and studies in the next slides. Again, on the one hand, the European Union, on the left-hand side, which means I will show you some general data, then some data based on this general data for steam generation, and also at the end for drying. And on the right-hand side, I will tell you something about a very new report from the International Energy Agency. The data for the European Union is mainly for the EU 28, as the data is normally used from periods before the Brexit. Coming to the general impact on the European level, that's an estimation from Andrew Marina, from a study from Andrew Marina. He states his estimation as very conservative, as just heat pumps are recognized for heat recovery with limits of maximum temperature, supply temperature of 200 degrees C, and maximum temperature lift of around 100 degrees C.
Son y media todavía.
Sorry, can you hear me? So this estimation is based on process data available now online. It's in a so-called bottom-up approach, and he states there are two different ways of the electricity supply. So on the one On the one hand, you have the current energy system, so that means the electrical energy mix, what we have now in the European Union, and he also stated a second scenario with a fully decarbonized electricity system, which is very interesting because in Austria we have very detailed plans to have a fully decarbonized electricity system by 2030. The author of this study also states that decarbonizing electricity is the most promising way of decarbonizing the industrial processes. On the left-hand side, you can see now the result. He estimates that with the current energy system, roughly 37 million tons per year of CO2 emissions can be saved. And with a fully decarbonized electricity system, around 52 million tons per year. On the right-hand side, he used different cost estimations of manufacturing costs of heat pumps. And in the study, it's estimated that around 4.6 to 11.5 billion euros will be used, which is a very, very good market and very significant share of market for the future. That's the general data. At the next slide, I will show you the share of the low pressure steam up to 150 degrees. Because if you look at the data from Andrew Marina, then you see that a lot of processes are using steam, some of them above 150 degrees C, but a lot of processes using low pressure steam up to 150 degrees C. And if you use the data, then you come up, then you can estimate that for the future heat pump market with steam generation, you have around a share of around 3.5 to 8.6 billion euros, depending on the costs of each heat pump. And you have the potential of reduction of CO2 emissions of about 21 to 35 million tons per year. On the left-hand side, the blue bar represents roughly the share of steam generating heat pumps in the overall market of this study. Coming to the drying processes, that's another way, another study you can find in the web. So it's the utilization of heat pumps in industrial drying processes, and these effects were published compared to the European targets of 2030. The author also refers to a very conservative approach, and it shows the relevant share of reduction of energy, primary and end energy, and CO2 emissions. They also use a top-down approach with the statistical data of the European Union. And they also use a very unfavorable share of emissions for the electrical energy system, because it was taken out from standards, which has very higher values than the average of the European Union. So I guess that's the reason why it's called very conservative. And this also shows at the end a very significant share of contribution of heat pumps to the primary on the top, primary and energy on the top of the graph of the slide, and to a significant share of contribution to the CO2 emissions of the European Union. As I said already, stating a very conservative estimation. Coming to my nearly last topic, so that's the world market outlook. It's a pretty new study from the International Energy Agency with a very interesting part of the industrial energy systems of the future. It's mainly in 2 slides for today. You can see that this orange part, so this orange part in 2030, this orange part is then stated from the International Energy Agency for heat pump, industrial heat pump. And in 2050, it's much bigger. So they expect that we will see a market which will grow very fast and coming in the next years. Just to give you it's a sentence out of this study, which is very, very interesting. So the International Energy Agency estimates that for low and some medium temperature heat, that again, the electrification includes an important role for heat pump, the electrification for decarbonization. And it's also, the second sentence is that they estimate that around 500 megawatts of heat pumps need to be installed every month in coming years, so in the next 30 years. And that looks for a very interesting market share in the future. So that's my main messages from today. Thank you very much to the co-author and to the help from my colleagues. And thank you very much to you for listening.
Okay, thank you very much, Franz, for your presentation. Now the floor is for Tommaso Ferrari from Turboden. Okay, so Tommaso, you can share your screen.
Yes, hello, good morning, everybody, and thank you for the introduction. I will now share my screen with you. Hopefully, we will not have any problem. Let's see. It should be online,
yes.
Right?
Yes.
Perfect. Okay, so my name is Tommaso Ferrari. I'm sales engineer at Turboden. And today I'm gonna give you a quick overview about organic Rankine cycle technology. We will have then a session in the afternoon from Tsupras connected closely to the specific application that we are developing in Bamboo project in the petrochemical sector. So this morning I will just focus on the ORC technology, providing some example of applications in industry in general and not just in the petrochemical sector. Before getting started, just 2 words about Turboden. Turboden is an Italian firm founded in the 80s, and since then the company has been designing and supplying organic Rankine cycle technology. So this is the main business of the company. And from there, let's say the company growth, developing also new products that are available now in our technology portfolio. And let's say that we are one of the world leader in the supply of organic Rankine cycle technology, and now part of Mitsubishi Heavy Industries. As I said, today I will just explain a bit the technology, how it works, and then provide some examples of the technology and how and where it can be applied. So first, the name, very simply, the ORC stands for organic Rankine cycle. So we are referring to a thermodynamic cycle, which has the same name of traditional Rankine cycle using water vapor. The name organic refers to the fact that here we have a thermodynamic cycle which uses an organic compound as a working fluid instead of water. We can have different organic fluids within the cycle itself that are selected time by time in order to best fit with the heat source used to produce electricity. Basically, the thermodynamic cycle, the organic Rankine cycle, works very similarly to the more traditional water steam cycle that most of you probably know. So we have a heat source that is used as, let's say, main power source. Then we have the thermodynamic cycle, the ORC cycle itself, which is a closed loop taking this thermal power from the heat source. And then we have a cooling source, a heat sink, where the power that cannot be converted to electricity is dissipated. So the basic mechanism is the same as many heat engines. We have a heat source, we have a cooling media, and in between we have a thermodynamic cycles with some components building the cycle itself. So the thermal power is taken from the heat source available and is drawn to the ORC cycle. Within the ORC cycle itself, we have, let's say, a component, which is the, let's say, the preheater and the evaporator that takes the thermal power from the heat source and heat up and evaporate the organic media that we use within the cycle. So we have this vapor at high pressure, which can be expanded in a turbine, an organic Rankine cycle turbine connected to the electric generator to generate power. Downstream the turbine, we have a couple of components. One, which is called the regenerator, to do, let's say, internal heat recovery and enhance the overall efficiency of the cycle itself. And then we have a condenser, where the heat that can be converted into electricity is dissipated to the ambient, either through a water cycle, let's say a water loop, or directly to ambient air. So basically, the overall functioning of this cycle is very similar to what is steam cycle. The main differences are come from the features of the organic compounds that an ORC cycle uses instead of water. So in these graphs, you can see the let's say TS graphs of water and atypical on the left, water, and on the right, a typical organic compound. Where you can notice some differences, let's say, in the overall shape of the cycle itself. The main difference, as it is highlighted here in the graphs, stands in the expansion segment, let's say, so from 0.3 to 0.4, which, let's say, has some differences if we compare an organic Rankine cycle to a traditional steam cycle. So in a steam turbine, we have, let's say, a high enthalpy drop, and due to the fact that the, let's say, the curve of the water is, let's say, has this shape of a bell, the last part of the expansion, which is here around in 0.4, let's say, can be somehow problematic, since it can finish either in or out the, let's say, B phase region here, depending on the actual conditions of the cycle itself. And this is, let's say, something that it is characteristic of water, and must be managed. In organic Rankine cycle technology, due to the fact that the curve here of the fluid has this particular shape, where the two lines dividing the liquid phase from the B phase, liquid and vapor phase, are parallel together. We have that the expansion here in the turbine, so the segment 3 to 4, is always in the dry region. So it is always in the vapor phase, and there cannot be any, let's say, condensation during the expansion phase of the cycle itself. And this, let's say, is a good point that simplifies the technology in many aspects. First, in the turbine, which is, let's say, more simple. There is no risk at all of condensation in the turbine itself, since the last part of the expansion itself is always in the dry vapor phase. So we have no erosion of plates, and this, as I said, simplifies the overall cycle itself, because this means that we don't have to reach specific conditions of the vapor at the inlet of the turbine to ensure that the expansion is dry, because the expansion will be dry in any case. So basically, let's say, as long as we have vapor at the inlet of the turbine, we are sure to have vapor also at the outlet of the turbine. This, of course, helps the cycle and the components associated to the cycle, because let's say no erosions means a turbine that does not have any overhaul during its lifetime. So the operation and maintenance associated to the unit is, let's say, quite simple and not expensive. And further to this, the fact that the let's say molecules composing the typical organic fluids are quite high mass molecules. We don't have a big enthalpy drop. This means few stages in the turbine, just 4 or 5 stages are enough to produce, let's say, an interesting amount of, let's say, mechanical power and therefore electrical power. So small and compact turbine, and at the end of the day also very good reliability and availability of the plant without need of a big O&M plan on the unit itself. The fact that, let's say, in point 3, so at the inlet of the turbine, we can accept almost any kind of vapor as long as the fluid is vapor, means also that we can adjust very simply, let's say, with an organic Rankine cycle, the evaporating pressure of the cycle itself. And therefore, changing this, let's say, plateau is not a problem for the unit itself. Of course, this is, let's say, an important aspect when we, let's say, talk about heat recovery from industrial processes, where the industrial process has its own, let's say, operating schedule that can vary during the day, because of the industrial process. So basically, the following a variable load with an organic Rankine cycle is typically easier compared to the a more traditional steam turbine, since let's say it is quite easy to, let's say, adjust the evaporating pressure of the organic Rankine cycle to follow the heat available from the heat source. And again, this is very important when it comes to heat recovery from industrial processes, which are independent from the fact that there is a heat recovery technology downstream the process itself. Here you can see in this graph a comparison of the behavior of an organic Rankine cycle compared to traditional steam at partial load. So what we expect and what we've seen in some occasions, that the organic Rankine cycle can keep a higher efficiency compared to nominal when the functioning is no more in the design point, but it goes down because the heat source available is, let's say, providing less thermal power than the design point itself. At the end of the day, what I would say, let's say, about organic Rankine cycle technology is that it is a power generation technology capable to receive thermal power from a heat source that can be, let's say, any. Then we will see in a few slides some examples, and turn this thermal power into electricity in a very simple and flexible way. The fact that the loop itself is a closed loop using an organic compound means also that there is no use of water within the organic Rankine cycle. so there is no need of any water supply to the plant, especially if we are considering, let's say, a dry-cooled solution. And this might be interesting for such places where the water supply is problematic. Further to this, as I said, the system is generally quite simple in terms of components, in terms of management of the partial load. The system is fully automatic. So let's say there is really an ease of operation associated with the plant, which is again interesting if we are talking about heat recovery in industry, where the industry, of course, has its own manpower dedicated to the industrial process, and typically we don't want to spend time on the technology that does the heat recovery part. The dependability, so the availability of the plant is rather high. As to Turboden, we are quite happy with the fleet of our RC units, and we have an average availability higher than 98%. This on a statistical base on the units that we have installed in these last 30 years. And generally speaking, let's say it is a quite good technology to do heat recovery and therefore meet the demanding targets that we have now in terms of the decarbonization and so on. What about the possible applications and where we can think to install, let's say, an organic ranking cycle? Well, in Turboden experience and in these years, we have, let's say, somehow divided to two main categories of applications. One concerning, let's say, what is called renewable energy. So we have our renewable, let's say, thermal power source. And this is the case of geothermal plants, biomass plants, and also waste to energy. And then we have the category of energy efficiency, where there is an industrial process upstream, and there is thermal power available, waste heat available from the industrial process. And there we can think to use an organic ranking cycle to use this waste heat to produce power that can be either used at site to cover on consumption or dispatched to the grid. And the possible, let's say, industries that we, where we have developed projects and where in fact we can find some thermal power available in a good amount are cement, glass, and steel industries, of course. But then, as it is the topic of, let's say, the bamboo project in the oil and gas sector, in petrochemical facilities, but also in some other facilities of the oil and gas industry itself, so in the gas compressor stations, for example, and so on. And then, of course, why not considering combined cycles using organic ranking technology instead of the more traditional steam turbine. So now what I will do is to give some examples for each of these applications, just to give you a quick overview of these cases. And then we will go, let's say, quite fast through a few references that Turboden has, just to give you an idea of the, let's say, potential of this technology associated to some, let's say, reference industry that might be found in our countries. So, as I said, in renewables, we talk about geothermal, we talk about biomass and waste to energy. The idea for all these applications is the same. So we have thermal power available from a certain heat source, and we can build an organic ranking cycle to exploit this heat source and produce power. Depending on the temperature and the amount of thermal power available, we can, let's say, adapt the characteristics of the ORC unit and plant that we can build, but the mechanism is always the same. We have thermal power, we take this thermal power, we convert part of it into electricity, and we dissipate we reject some heat to the ambient according to what is the efficiency of the cycle itself. I can hear some background noise, so I can thank you. So concerning geothermal application, the main heat source is geothermal water coming from the underground. Depending on the characteristic of the geothermal reservoir, let's say, we have different solution, but generally speaking, any geothermal resource from 100 degrees C and above is, let's say, a possible, let's say, geothermal resource that can be used. And the most preferred solution we have for these plants is an ORC using air-cooled condensers, so not requiring water for the cooling. But again, different solutions are available. I will go quite fast on this since let's say the idea is quite simple. It's just some slideshow about examples. So in biomass, again, the heat source here changes from the geothermal reservoir to some waste biomass that might be available in sawmills or panel factories and so on. So there are many industries that process wood and have wood waste. What to do about this wood waste? One possibility is to burn this waste biomass into a boiler and with the thermal power feed an ORC unit to produce power. And in this case, the most interesting, let's say, configuration for the ORC technology itself is a CHP configuration where the ORC is capable to produce power, but also, let's say, reject it to ambient, to water at 80 degrees C, so that this hot water at 80 degrees C can be used by a thermal user requiring it at relatively low temperature, such as a drying process. And this schema is really typical of sawmills, for example, or in any case, industries using wood or biomass in their processes. And here on the right, you can see some example of possible, let's say, biomass fuel that we have used in our history and our plants. Waste to energy then is the same concept as biomass, just using waste. And we see this as a growing, let's say, sector, since, let's say, waste is one of the problems of our time, and the disposal of waste is, of course, let's say, a big topic. Let's say we have ORC plants working downstream big incinerator plants, as well as small ORCs using, let's say, directly the waste, the solid waste as fuel, as it was for biomass, just replacing biomass with the landfill waste and so on. Stepping to energy efficiency, let's say, applications instead. We have that, let's say, there are some industries having high temperature processes, and these processes have also, let's say, high temperature exhaust gas that can be exploited as a thermal power source to feed an ORC unit. So the main industries here are cement, steel, glass, and then, of course, oil and gas, which is a quite broad sector with many different processes And again, on the oil and gas part, we will have a dedicated session in the afternoon. The concept again is quite similar to what we have seen before. So we need something to capture the thermal power available and transfer this thermal power to the ORC unit itself. So there is an interface, let's say, between the production process and the ORC, which will be a so-called waste heat recovery unit, typically producing thermal oil, which is used as a heat carrier. And then this thermal power through the heat carrier goes to the ORC that will then produce power. With the same schema, let's say, as anticipated, we can think also about combined cycles using organic Rankine cycle. So there are many facilities still today working with open cycle gas turbines, mainly, for example, in gas compressor stations, but also in power stations dedicated to some industrial facilities, for example. And of course, you probably all know that gas turbines are known to be very reliable, but not that efficient in terms of, let's say, conversion of primary energy to electricity. Let's say ORC technology is suitable to exploit the thermal power available in the exhaust gas of a gas turbine, or also a reciprocating engine, to produce additional power. And if you see, for example, the case of the gas turbines, you can see that the amount of thermal power that the ORC is capable to produce is in the order of 30 to 40% the capacity of the gas turbine itself. So if we have a 10 megawatt gas turbine, the ORC is able to produce 3 to 4 megawatt, depending then on the operating condition of the gas turbine, of additional thermal power. Therefore, let's say, adding a quite interesting boost to the, let's say, electrical output of the gas turbine itself. So this was just to give you a bit of, let's say, an overview of the possible applications, just some example projects to have some numbers also, and not just general concepts.
Sorry, Thomas, there is only 1 or 2 more minutes.
Yeah, but it will be very fast. It will be just 2-3 slides to show some examples. Let's say in the industry mainly, since Bamboo project is mainly focused on the, let's say, decarbonizing, let's say, industry. So here is an example for a cement plant in Turkey, where the clinker production capacity, so the production of the cement factory, is in the 10,000 ton per day production. Here, by recovering it from the exhaust gas of the cement process, the ORC size is 7 megawatt. And therefore, if you consider this running for 8,000 hours per year, and comparing this with the intensity factor of Turkish electricity generation, you have a quite interesting, let's say, amount of possible CO2 savings. Actually, CO2 savings. This is a project that we have done of 25,000 ton per year. Similarly to cement, also the steel industry has some, let's say, quite good potential, meaning that electric arc furnaces have waste heat available. And here is a project that we have developed in Italy for Arvedi steel. And in this case, the ORC size is in the range of 10 megawatt of electricity dispatched to the grid by simply recovering, let's say, the thermal power available at the facility. In glass industry, this is another project we have done in Turkey. This is a, let's say, Kablik group, and from a, let's say, 1,200 ton per day glass production capacity facility, we have 6 megawatt ORC size, let's say, that we were able to install at site to to take advantage of the waste heat available in the facility itself. Last, an example project for, let's say, heat recovery from open cycle gas turbines in gas compressor stations. Here is a project that we've been recently awarded. It is a gas compressor station in Egypt, quite large, to be honest. And here the idea was to, let's say, in front of future expansion of the pumping capacity, gas pumping capacity of the station, instead of installing new gas turbines to extend the capacity of the gas compressor facility. The idea was to recover heat from the existing gas turbines, use ORC technology to produce power. Here we are talking about 2 ORCs of 12 megawatt each, and use the electricity produced by the ORC to drive gas compressor, electric motor driven gas compressors. So replacing new gas turbines with electric motor driven compressor driven by ORC units. Here, the last slide of my presentation, just to give you an idea of the, let's say, the projects that Turboden has developed in its, let's say, history, and how they are divided among the various applications that we have seen today. With this, I have concluded my presentation, and thank you all for the attention. I guess that for questions we will have a dedicated part later on, right?
Yes, we have a dedicated part at the end. There is in fact a question concerning your presentation, Tommaso. Okay, so we can better move with Erika, and at the end we can do the question and answer session.
Okay, thank you.
Hi, also from my side. Can you see my screen and hear me?
Yes, perfectly.
Okay. So good morning. I am Erika Pierri, a research associate at the Technische Universität Braunschweig in Germany, and I welcome you to the third slot of this webinar titled Energy Flexibility Strategies Contributing to Decarbonization and Renewable Energy Integration. So we first have a look at the outline of my presentation. I will start with a background explaining the key role of energy flexibility in the energy transition. Then we will know about a few facts about energy flexibility, first in general in the power system, and then more specifically in a production system. Then I will explain the potential to integrate energy flexibility in energy-intensive industries. We will have a short overview of the activities performed within the Bamboo project in this context. Finally, some challenges and opportunities to integrate energy flexibility in energy-intensive industries. And last, the conclusions of the presentation. So we start with the background. As you know, and as already mentioned by my colleagues in the previous sessions, if we want to achieve the ambitious climate targets, we need a transition from fossil fuels to renewable energy. An integration of renewable energy in the mix results, however, in operational challenges in the grid, because as you see here on the picture, the supply from wind or photovoltaics is not constant over time, but is rather volatile. So this results also in a volatile supply. Sorry, there is some background noise, I think. So if we want to encourage higher penetration of renewables, we need changes in the operation of the grid. And what's the role of energy flexibility in this? So on the supply side, an increase of flexibility can ensure a higher reliability of the grid. And on the demand side, so on the side of the consumer, they can also benefit from these fluctuations because it reflects in the fluctuation of energy prices. We have now a more general overview of the role of flexibility to fulfill the decarbonization targets. Here on the right side, you can see that there are 5 main industries, also called the Big 5 in manufacturing, that dominate the direct CO2 emissions worldwide. These are iron and steel, cement, chemicals and petrochemicals, pulp and paper, and aluminium, among other industries. And here, per definition, those industries are energy intensive. Their demand for energy is also constant, and they therefore rely mostly to fossil generation plants on site. So as you see here, there would be a high potential to integrate renewable energy. So if we have a higher amount of renewable energy in the grid, we could also integrate those energies in the production sector by substituting the fossil generation plants. And so this integration of renewable energy is a really promising solution towards carbon neutrality in the industrial sector. So if we now have an overview of the different types of flexibility in general in the power system, we have mainly direct and indirect types of flexibility. So the first type of flexibility is a direct flexibility, which occurs directly on the supply side by flexibilization of the power plants or curtailment of renewable energies. And this type of flexibility is already implemented, is already occurring today, and is quite cost effective. If we want to now have a look of more recent flexibility technologies, we have the storage flexibility that can be enhanced through centralized or decentralized energy storage system. This is still cost intensive, but it allows seasonal balances. Another way to balance some imbalances that we have in the grid is to expand the transmission or the distribution networks or develop smart grids. So this would be the flexibilization of the transmission grid itself. And this, of course, it's also intensive because it comes with the expansion of the grid, but it allows to reallocate a surplus of energy between regions. Then we have a fourth type of flexibility is the demand-side flexibility, with such terms you might have heard as demand-side management and demand response. And this can enhance grid stability. So from the consumer side, we can support the stability of the grid, but here we need operational changes in the production sector. The final type of flexibility we can mention is the so-called intersectoral flexibility that can be enhanced through such technologies categorized as Power-to-X. And this is also a way to enhance grid stability and to increase sector coupling. So now that we had an overview of the types of flexibility in the power system, we can focus on the production system. So we can define energy flexibility of a production system as the ability to react to changes in the electricity supply in a rapid way with low financial efforts and without compromising the product quality. So we can say that in the production sector, there are three dimensions of flexibility, or when we want to implement flexibility strategies, we have to take into account three dimensions. The first dimension will be the state dimension. So we would need to adjust the operational state of the machines or of the assets, and so to adjust the power demand. The second dimension would be the time dimension. So when we want to implement the flexibility strategies, we have to take into account the time frame that it takes to implement the strategy. And finally, of course, this comes also together with some costs that should have a positive impact. Also, in a production system, we can distinguish between different types of flexibility that directly or indirectly affect the performance of energy flexibility. So the first type of flexibility in a production system is the so-called volume flexibility. So we could, for instance, change the output quantity. So we could reduce the number of products that are produced. We can change the route. So we can, for instance, switch off a machine and use another machine to produce the same product. We could think about adjusting to the market demand, so to produce alternative products. And if we do that, then of course we have also to adjust the machines to these new products we are producing. And the final type of flexibility is a rather organizational strategy, and it is to reorganize the working hours and the schedule of the personnel. so the so-called personal deployment flexibility. So now that we had a look of all these types of flexibility, we can see that if we want to implement or enhance those flexibility, we need different strategies. And here I want to give you an overview of what these strategies could be. So first of all, when we want to implement the flexibility strategies, we can do that at different levels of the manufacturing system. So first of the manufacturing system itself, so in the factory, that would be the lower level of the pyramid. Then we go in the upper level, the operation and control, and then to the business planning and logistic. And the higher we go in this pyramid, the longer it takes to implement a flexibility strategy. So here we give you a short overview of each level. So in the manufacturing level, we could think about interrupting some processes in some minute to hour time frame or changing the process sequence. And if we go in the upper level, strategies might take longer, so day until up to weeks. And that would be to also interrupt the process, but for longer time frames, or storing energy or changing the energy source. And in the last level, if we go on then to the logistics, so to a more longer term planning, then we could change the production order even, or adapting the machine loads, or adapting the shifts. So as you see here, we have different strategies that can be implemented. And these strategies can be or are defined for a production system in general. But if we want to really assess the implementation potential, we have to take into account that there are some restrictions that must be considered. So we have first the theoretical potential, which is basically the strategies that we can implement, taking into account the power load we have. And among these, then there is the strategies that are technically feasible. And within the technical feasible strategies, then we have to take into account some economic restrictions and some other restriction that might be organizational or from restriction imposed by local regulations. And the intersection between the economic potential and the practical potential is the viable potential. So this would be really the strategies that can be implemented if we take into account all the restriction and the constraints. So now that you have all these definitions and you have learned about the different flexibility types, I want to tell you or explain what are the challenges of implementing energy flexibility in energy-intensive industries. And to do that, I would like to explain first the difference between general manufacturing system that would be discrete manufacturing, like if we take as an example the automotive industry. Here we would have as input products that come from other manufacturing processes, so some parts of a vehicle. Then we have a reversible assembling of this vehicle, and the final output is then, for example, the car. If we see, on the other hand, energy-intensive industries, also called process industries, here the raw materials, so the input, are mainly of natural origin. So if we think about, for instance, the pulp and paper sector, the main raw materials is wood. So then we have an irreversible transformation from a material that is wood to, for instance, an output product that will be a paper roll. So in the energy-intensive industry, the main characteristics are that the process is continuous. The factories run usually 24/7. They are by definition energy intensive, and therefore, due to this continuous demand and intensive demand, they rely still nowadays to fossil fuel-based generation. So here you see that there is a high potential to integrate renewable energy. And renewable energy, of course, it always comes coupled with implementation of energy flexibility, which is indeed more challenging in the energy-intensive industries as in discrete manufacturing sector. And this is what we have been doing in the second pillar of the Bamboo project, in the electrical flexibility pillar. So here I would like to give you an overview of three main strategies and technologies that are most promising in the energy-intensive industries. The first is the so-called demand-side management that I was mentioning before in my presentation. So demand-side management can be defined as a set of customer end strategies to provide flexibility in the balancing market, either by decreasing the demand through strategies as peak clipping or energy efficiency, or by shifting the energy consumption through valley filling or load shifting. So through, let's say in general, flexibilizing the shape of the load. Energy-intensive consumer have a constant and high base load, as I explained in the previous slide. The energy-intensive industry offer a really high potential to serve as a capacity reserve for the grid. So if we want to increase the share of renewable energy, both in the grid and in the industries, we have to take into account the main challenges that come with integration of renewable energy. That would be the temporal variability, as I showed in the early slide of the presentation, the uncertainty, the geographical variability, so that they are really depending on the location and on the weather conditions. They're usually decentralized and they are non-dispatchable. So if we integrate renewable energy in energy-intensive industries, the operator have to cope with this lack of controllability and reliability of supply that this might come. So if we then couple the integration of renewable energy with energy flexibility, not only on the grid side, but also on the demand side, so on the production system itself, this would enhance better or more reliable operation of both the grid and the industrial process. And there are, we can think about two ways of integrating renewable energy. The most common way that you could think about would be to install new assets on site. So a power, photovoltaic panel or a windmill. But actually, even more promising solution to that would be to acquire excess of renewable energy that is already available in the grid and substituting on-site fossil fuel plants by this excess of renewable energy through contracts such as power purchase agreement. And you will hear more about this in the afternoon session by the UPM case. Another technology that can enhance flexibility and more specifically demand-side management is the installation of energy storage systems. So energy storage system can be classified into mechanical and physical, such as compressed air or pump hydro, electrical, such as capacitor and supercapacitors, electrochemical that are more common, like batteries and fuel cells, and thermal energy also. And the way of helping or supporting demand-side management is that in times of lower costs or in times where we have a higher availability of renewable energy, we can charge the storage system. And then in times where the prices are higher or we don't have availability of renewable energy, then we can discharge the system and use this energy in the production process. Another technology that has been already mentioned by my colleagues in the previous session is the integration of waste heat recovery technologies to increase energy efficiency. And as you might remember from the picture I showed before about demand-side management, energy efficiency also indirectly affects the overall energy flexibility. And this was what was done in the first pillar of the project. So I won't go into the details here. Here, just a short snap of an assessment we have performed within the Bamboo project. So we have divided mainly the production process into 4 levels. So we have the factory level in general, then we have the technical building services for the provision of energy, the production units, and the machines or the assets. Then we have created a catalog of different strategies that can be implemented in the different levels. We have evaluated the impact of those strategies on energy efficiency, flexibility, or demand-side management more in general. And finally, we have evaluated the feasibility of implementing those strategies at each level. And if you're interested in the assessment, you can have a look at the reference. You can find in the reference list It was a publication we have published within the project. So now just a general overview of the activities carried out in the project in the context of energy flexibility. The main focus of electrical flexibility was in the pulp and paper sector. And here we have carried out different activities. So in the early stage of the project, we have been focusing on the identification of energy hotspot and also on the potential to recover process heat to, in general, boost energy efficiency. More recently, we are working on the flexibilization of the heat and power supply, and we are assessing the integration of renewable energy, power to heat, waste heat recovery, and storage systems. And we are doing this with the support of forecasting models, which are performed by our colleagues at Enside, and by simulation models for long-term production planning. And the idea is to integrate energy flexibility in the production planning. And with these activities we are performing, we are trying to contribute to the grid flexibility and also to decarbonization of the industrial sector. And you will hear more about all these successful cases and results in the afternoon session by the UPM case study in the pulp and paper sector. So what are then the challenges and opportunities of energy flexibility in the energy intensive industries? So the main challenges is that, as you have seen, the applicability of this action is very complex in daily practice, and it requires really changes in the production sector. When we think about the installation of new energy assets or storage technologies, of course, the investments that are required are still very high. And beside storage technologies come also with high environmental impacts. On the other hand, if we integrate renewable energies and we substitute the fossil fuel generation, we would have a higher environmental performance in the energy supply chain and consequently in the production process. And the consumers can benefit from lower energy prices and can create new business models for the energy supply system. Here I come already to the conclusions of my presentation. So as I was mentioning in the beginning, if we want to reach the ambitious climate targets, we need a transition from fossil fuels to renewable energy. And this transition comes, of course, with operational challenges in the power system that can be overcome only by increasing the overall flexibility of the power system. If we want to overcome these problems through electrical flexibility, all the actors have to contribute. So not only from the supply side, so from the grid side, but also from the consumer side. And here we have been focusing mostly on the consumer side, so on the demand side flexibility, and we have seen that there are different strategies that can be implemented to enhance energy flexibility on site, so in the production process. And the most promising strategies that I have mentioned were demand side management, integration of renewable energy, and energy storage system. But of course, in order to implement those strategies, in the energy intensive industries, we have to take into account that the strategies are really dependent on the process, and we have to analyze the production process and its characteristics in details. So that's basically what we have been doing so far in the context of energy flexibility in the Bamboo project. I thank you for your attention, and here I leave you some references for further readings. Thank you.
Thank you very much, Erika. Now is the turn of my colleague Anna from CICE, who will explain the flame monitoring activities performed within Bamboo. So the floor is yours, Anna.
Hello, good morning. Let me share my screen.
Yes, we can see it.
Can you see? Thank you. Hello, good morning to everybody. Thank you for attending this talk. I'm going to present the flame monitoring system, and I'm going to explain how it works and its benefits, and how we are applying that technology in the Bamboo project. So let me introduce myself. My name is Ana Gonzalez. I work in CIRCE as Technology Service Manager for image-based diagnosis. My background has been focused in the last years in the use of flame images to develop combustion monitoring tools using artificial vision and machine learning models. This development has been applied in different sectors. We have been working in the glass industry and also in the petrochemical sector. And this work during this year, we have been working with different fuels, with natural gas, and also with blends with hydrogen, and also with coal and torrefied fuels. Thanks to the experience, we are part of the Bamboo project. In this project, we are working in the waste stream valorization pillar, in particular in the steel sector. The energy industry, intensive industries are exploring different approaches to achieve the decarbonization of the sector, and it's a very challenging objective. And in the Bamboo project, the idea is the introduction of new fuels for the combustion and to generate the energy. In this case, processed gases is used for this aim. And this kind of new scenario can present and generate some uncertainties to how to manage these new fuels and so on. And the flame monitoring system that we are developing intends to support this new scenario, this new fuel combustion. So the goals of this technology is to increase the efficiency of the process, and of course a reduction that leads to a reduction of the emissions. How can we get that with this technology? Thanks to that, we are going to control more precisely the combustion, and thanks to this tool, we can detect malfunctions and inefficiencies in the burners, and also we can reduce the fuel consumption, and in that case we can help to a reduction of that uncertainties that arise in this application. Let me explain the technology itself. This is a sketch of the common general industrial combustion system. You have the different parameters that you can measure, that the temperature, flow rate, airflow rate, emissions, and so on. And in our case, the technology integrates a visualization system to see what is happening inside the furnace in terms of the flame, what is happening with the flame. And this technology can automatically analyze the future of that flame and can generate a huge quantity and valuable of information that it will use to improve the combustion control, because with warnings and predictions, the combustion will be diagnosed. In the Bamboo case, this technology is applied to different fuels. And in this case, you can see different flames of fuels. One of them, the top of the image, is the process gases, and another one is the natural gases, or the natural gas. So the type of the flame is highly dependent of the fuel and the combustion condition. So the core of this technology is to detect digitally and automatically those differences using image processing and machine learning models to forecast key parameters and the behavior of the combustion. This work in the Bamboo case is going to be applied, or it's being applied in two different scales. We are working at laboratory scale in CIRSE facilities with a research type of environment to go deeper in the combustion processes. And also we are working in a semi-industrial scale and Arcelor facilities. So this technology is meet the decarbonization on the industry through the digitalization of the combustion processes, and allows to advance to the industry 4.0. The use of the machine learning model and the image processing can help to the detection of combustion inefficiencies and help to optimize the combustion through generating warnings, alarms that can be used for a better management of these processes. The benefits of this technology is focused on the cost reduction, because the optimization of this process can lead for a reduction in the fuel consumption, and also that allow a lower pollutants generation. And finally, in this technology, increase the safety of the operators, because at the end you have eyes inside the furnace and you can see what is happening, and warnings and different key parameters can be provided to the operator with in such a manner that the visual inspection can be diminished. So for all these reasons, we can say that this technology meets the objective of zero emissions industry. So thank you very much for your attention. If you have any question.
Okay, thank you very much, Ana, for this very interesting presentation. Now is the turn of Luis.
Yeah, good morning. Can you hear me?
The foundation. Yeah.
Okay, I'll try to share my screen now. Okay, so you should be seeing my screen and also my muse, right?
Yes. Yes.
Okay, perfect. So, good morning, everybody. I'm Luis Perez. I'm head of the simulation group of CIRSE, and I'll try to explain first what is CFD and then how we use it within the Bamboo project to support the decarbonization of the different sectors. So, for the part of the audience that has never heard about CFD, please give me a couple of slides to show you what's hidden behind those three letters. And yeah, those three letters. And also why I find CFD so useful and so cool. CFD stands for Computational Fluid Dynamics, and basically is a bunch of computational techniques to model the physics that rule the movement of fluids. Using CFD, we can model, for example, the interface between one fluid and another, including all the laminarization and turbulence processes. We can model the mixing of different jets. This image here is much more like a marketing image, but we can think about streams of different species or different temperatures. We can model combustion, transient happenings like flame liftoff or steady state radiative heat transfer. And we can also model pollutant formation, which is particularly interesting in a case like the one that covers bamboo, which targets to reduce emissions. So actually, CFD is not new. The equation under all these phenomena have been terrifying or exciting engineers and scientists for 2 centuries now. Even though the Navier-Stokes equations are still unsolved, and in fact, there is this Clay Mathematics Institute which named them one of the 7 most important open problems in maths, and there is a prize of $1 million for whoever finds a solution or a counterexample of these equations. So since 1822, a lot of things happens. First is that now, in case you finish this talk with fluid dynamics, you can have these equations imprinted on a t-shirt. But anyway, I'm not going to get into capitalism this early in the morning. So the second one, and most important for us today, is computing. Even with the current shortage of semiconductors, computation has become cheaper and much more powerful. And that allowed CFD geeks to model and solve their problems much faster, much cheaper, and targeting bigger and complex installations, such as the ones that we find in the industry. So this development of computers and solvers demonstrated that CFD is ready for industry, and which is most important, is useful and cheaper than traditional experimental campaigns and design cycles. The virtual models that we develop with CFD give a complete picture of the inners of processes and industrial assets, and they allow designers and plant operators to study different scenarios and modifications to achieve their goals faster and also without risking their production or installation. So going back to bamboo, we'll try to explain how CFD has been used to reduce emissions and boost the flexibility of 3 different case studies for these 3 energy-intensive sectors, has been said during this morning, which are the steel, mineral sector, and paper and pulp. Then at each demo site, we applied different approaches to reduce fossil fuel dependency. Sorry. All of them go around combustion and how it changes when we modify the fuel. In the case of steel, we studied the effect of a residual process gas. In the mineral sector, we focus on biomass. And for paper, we increased the share of our residual sludge with special interest in the moisture content. So now I'm going to get deeper into each demo site and explain a little bit more what we achieved. First, the steel sector, as my colleague Cristina already explained, we tried to replace part of the natural gas with one of the residual gases that they obtained in the plant. So together with ArcelorMittal, we ran an experimental campaign at a pseudo-industrial testing unit that they have there. And in that unit, we ran this campaign and validated our models. So right after that, we started executing and solving different cases with different fuel cells, preheating, and even with oxygen enrichment. Those three factors are what we call the model inputs, and which can be evaluated thanks to the CFD model. And we analyze the results of these different inputs through the model outputs, which in reality are much more than these ones, but these are the ones that we targeted. And well, obviously, different fuel cell or preheating or whatever, it changes the flame geometry, changes also the heat transfer and the formation of pollutants, of nitrogen oxides and so on. So let me, here we have hidden the color map and part of the geometry due to confidentiality, but these images I think that will serve to at least give an example of the kind of results that we can obtain with CFD. Here we can see, let's say that these three rows here correspond to different inputs. And we can see how variation in these inputs resulted in different flames, different temperatures, and also different flow patterns. In fact, they are totally different, these jets from this other. So, of course, beyond these images here, we can also obtain the response in terms of emissions and heat transfer to the load, for example. And another interesting thing about CFD is that it allows us to study scenarios beyond what is feasible in the real installation. So let's say Arcelor will need much more residual gas to achieve the temperature that they will need in the installation. For some cases, that's even more than the amount that the installation could provide. So at CFD, we don't mind about those limits, and we simply set the mass flow and study the results, and then let the process engineers worry about how to achieve that flow. Then for the mineral sector, Göresian magnesites went for biomass to reduce coal dependency or coal consumption. In this case, the industrial furnace was used for trials and also studied in the CFD model. And in that industrial furnace, different shares of biomass and different types of biomass were tried. And of course, that also affected the flame, or will affect the flame geometry, heat transfer, and emissions. So if you find this interesting, you will love the next talk by Nicolas, because he's gonna talk about these kind of biomass effects. But I also wanted to include some images to see what we are talking about here. So here you can see a sample of the temperature contours obtained in the installation. Once again, sorry, but no legend or geometry is available. So thanks to CFD, we can study the current situation and then introduce more and more biomass while trying to keep the things the way they were with coal or before those changes. So let's suppose that here in the middle, we have the current situation. And above that, on top of that, we have one of the biomasses tried and different shares. And on the bottom, another type with different shares. That way, we could analyze the results and find several cases which should be considered similar to the original case and which are interesting to be tested or even not to test because they could be really risky for the installation or for whatever and damage the furnace. So as I said, you should listen to Nicolas if you are interested in this biomass process. Then for the paper and pulp sector, well, this one is by far the hardest one. Here we have to model a challenging combusting unit, fluidized bed boiler. Well, in short, a fluidized bed boiler has a large amount of sand suspended, and this sand is started or let's say preheated with natural gas, and then different types of matter are introduced there and burned. This kind of equipment is quite common when you want to valorize things that still have something to be burned, but are not that good fuels as coal, natural gas, biomass, and whatever. So the problem here for CFD and for us is that a precise model involves a lot of complex phenomena happening at the same time. You will have the bed fluidization, different combusting particles, radiation and heat transfer, of course. And on top of that, these phenomena must be treated as transitory. So here, UPM targeted residual sludge to be valorized, but they were worried about the effect that the share of this sludge will have in the unit, and also the effect of the moisture, since it could affect also the dynamics of the fluidized bed boiler and the system temperature. So, well, that's what we are trying to solve by means of CFD. The fact here is that even with powerful computers and all of that, as I say, not everything can be solved with the required precision, at least yet. So this work is still ongoing, and we are trying to acquire data from that simulation and try to simplify as much as possible the happening inside this fluidized bed boiler to study and see how the different shares of this sludge and its moisture will affect its behavior. And sorry. And then, yeah, what we are trying here is to model, even if it's an approach to the CFD or the complete problem, and then learn from that simulations and develop this kind of simpler model. And finally, now that you are all CFD experts, you could say, okay, but that's a classical CFD analysis of 3 different cases. So where is the innovation that an European project requires? And yeah, exactly, that's what we want to obtain goes further. We are trying to develop this kind of ROM, this kind of reduced order models, which are, let's say, blocks or black boxes capable to obtain real-time results upon input modifications. So let's say that when you have a ROM, you can specify some inputs and obtain the resulting outputs according to what you did before. So that's also a very challenging development, especially for combustion, because those ROMs require a large amount of studies and solver optimization to not waste so much computational time. Our ROM creation starts from the CFD models that we were talking about and its validation, and then we have to run several cases covering the input variation ranges. Then we use sophisticated algorithms to find hidden laws between these inputs and the outputs. And finally, what we do is obtain a standard format easy to be plugged into a DSS or a control system, or even into a bigger digital twin of the plant or whatever. And okay, maybe I went too fast, but since I think that we don't have time for questions, here you can find my contact details. And of course, if I will be more than pleased to discuss any of these topics or any recent doubts. Thanks for attending and have a fruitful week.
Okay, thank you very much, Luis. In fact, we will have some minutes for question and answer at the end of this morning session. So now is the turn of Nikos from third. Nikos, we cannot hear you.
Hello.
Yeah, now we can hear you.
Nikos Margaritis from Research Associate in Center for Research and Technology Hellas. Can you see my presentation? The first page, the first slide?
Not the first, but content.
Okay, it needs some time to load. I will. Okay. My presentation is about biomass as alternative fuel and co-firing in low NOx burners. Contents of my presentation are the decarbonization of energy-intensive industries, some words about use of biomass as alternative fuel, techniques for NOx reduction and technology of low NOx burner, and last, types of commercial low NOx burners for the different technology providers and applicability in mineral sector and GM. The top priority for the EU member states is to foster, as we all know, growth and competitiveness to sustain and strengthen recovery and to achieve the goals set by the EU. So we want a low carbon economy, which means 80% reduction in emissions by 2050. CO2 emissions in case of magnesia industry derive from fossil fuels, which are related to their production processes. This type of emissions must be tackled so that these industries, although partially guaranteed by free CO2 allowances until 2030, the target is not to face issues due to continuous increase of CO2 prices. As we see in the graph next, we see that the carbon market price is always increasing in the last months. So today is around 51, 52 euros per ton. So this is a difference.
Sorry, can you please change into presentation mode, if possible?
Now?
Maybe it's loading.
Okay, this now is full screen. Okay.
Not for me, Cristina.
I think it needs some time.
Okay, now it's presentation.
Okay.
Yeah, thank you.
So, taking into account that this always increasing carbon market price, we should do something in order to mitigate problems of CO2 emissions in the future. So the solution to this problem is the use of biomass. So this partial substitution of current fuels with biomass could be an option in the future. EU has started a progressive decarbonization with the aim to become, as I said before, carbon neutral by 2050. Energy-intensive industries are expected to play an important role in this transition, as they represent a big amount, 24 amount of the final energy consumption. Here we can see the short-term vision and the long-term vision. Short-term vision meaning 2030 and long-term vision meaning 2050. So the technology options for the short-term vision can be are conventional renewable heating through biomass, bioenergy carriers, solar thermal, geothermal, and a target is to have renewables use as to increase the renewable use, but now it's below 50%, And the low-term vision is to use conventional renewable heating and power, also new renewables, solar thermal, biosyngas, hydrogen in the mixture, and also synthesis fuels from renewable-based hydrogenation of CO2 capsule. So the target is to have 100% renewable use until 2050. Also, you see here in graphs that bioenergy offers the EU a reliable vehicle to achieve carbon neutrality by 2050. And we can see here the evolution of the final consumption of bioheat by sector and specifically the industry in EU 2028. If we see the European Green Deal call in the Horizon 2020 and the future calls, we realize that energy-intensive industries such as steel, chemicals, and cement are key to Europe's economy, and they account for 20% of EU's greenhouse gas emissions. It's worth referring to targeted impacts in the Area 3 industry for a clean and circular economy, and especially Impact 3, 4, and 5 that talk about reduction of industrial CO2 emissions, improvement of air quality, and contribution to industrial circularity in order to meet greenhouse gas emissions. So biomass, as I tell you before, it would be an option because it has environmental benefits, economic benefits, but also some challenges that have to be faced and more effectively. Regarding the environmental benefits, when we use biomass, we conserve non-renewable resources, we reduce the waste disposal requirements. This contributes to lowering CO2 emissions because we replace a fossil fuel with biomass, and maximizes the recovery of energy from waste. Also, there are some economic benefits when we use biomass, because burning biomass as a source of energy could save significant costs and save foreign currency by replacing imported fuels. Also, there are some possible transport-related benefits if local alternative fuels replace imported fossil fuels. The cost can be lower if we use fuels that we have near the factory. Then it is worth doing a biomass supply chain in order to cover the needs of the factory. The challenges, although that they exist in the biomass sector, and it's very difficult to implement in full scale, is that usually the implementation of effective fuel supply chain is difficult. In order to ensure needed quantities and the appropriate size of biomass, and also in affordable cost for the final users. This always have some problems that need to be tackled in order to avoid future problems. And also another challenge is to use problematic cheap agrofuels that have some problems because they have high RAS contents and they're not easy to treat. So there are some processes like torrefaction that end users can use in order to increase the properties of these fuels and to have better results in their processes and lower CO2 emissions. Torrefaction may become a strategic alternative when fossil fuel costs and CO2 allowances prices are high. Then it's worth doing a process like this. Increased environmental performance at a modest cost is one of the drivers for biomass coal co-firing. Biomass usually has lower sulfur content than coal or coke, so co-firing results in reduction of SOx emissions. Also, the addition of biomass can be shown to reduce NOx emissions, and the high volatility content of biomass can effectively establish a fully rich zone early in the flame that can reduce also NOx emissions. Regarding the types of NOx emissions, we have three types: thermal NOx, fuel NOx, and prompt NOx. The concentration in thermal NOx, the concentration of thermal NOx is controlled by two factors: combustion temperature and the availability of nitrogen and oxygen molecules. Fuel NOx is produced by the oxidation of fuels, such as coal, that contain already ionized nitrogen at temperatures greater than 750. And prom NOx is a third category of types of NOx emissions. It's formed from molecular nitrogen already available in the air in combination with fuel-rich atmospheres which exist in almost all combustion processes. There are some techniques for NOx reduction. They're categorized as primary techniques and secondary techniques. Process optimization, improved firing technique, stage combustion, and better design are the primary techniques, whereas selective non-catalytic reduction and selective catalytic reduction are categorized in the secondary techniques. Here we can note that according to the BAT reference document for the magnesia sector, NOx emission limit for the high temperature DBM process in magnesia sector is 1,500 as a daily average value. But if NOx is left unchecked, then emissions can be higher, almost 3,000 or higher. Regarding secondary techniques, as I said, there are the SNCR technique and the SCR technique, but these techniques are difficult to be used because there is a temperature window 900 to 1100 for SNCR, and the temperature window for SCR is 300 to 400 Celsius. So you have to be in this temperature window in order to accomplish reduction. This is the problem with the magnesia industry, that not always you have these temperatures in the flue gas in order to achieve the reduction. And among the primary techniques, technology that is effective is the technology of low NOx burners. Regarding low NOx burners characteristics, we can say a few words about the main principles. It's a stepwise combustion which delays the mixing and input of fuel and air at appropriate stages in order to achieve a controlled combustion process, and this results in a fuel-rich flame core and lower peak temperatures. First generation of low NOx burners applied to furnaces were using the basic principle of phase staging. Now, the new generations of low NOx burners applied to heavy industrial furnaces, they use not only the technology of phase staging, but also the fuel staging. This means that they use very specific fuel injection points, which helps to reduce the NOx emissions in the process even further. The hardware used to influence the fuel mixing varies from manufacturer to manufacturer, and the percentage that the NOx reduction can provide, the low NOx burners can provide a NOx reduction until 50% or more, according to the specific process and manufacturer. The last section of my presentations will be about the major NOx burners, low NOx burners technology providers. If we want to categorize these LNBs, we have three categories according to the technology providers in the market. So we have category 1. The main characteristic, because I don't want to bother you with very technical details, but the main issue here is that the primary air is divided at the burner inlet into axial, radial, swirl dispersion channels. The amount of air going through the respective channels is adjusted by valves, etc. And in this category, we have these technology providers, Greco, D-flame burners, FCT combustion with turbojet AF burners, and we see that all these manufacturers they offer a loan of this technology that can be used for all industries: cement, lime, iron, cowling, and they can use these burners different alternative fuels such as RDF, biomass, sewage sludge, rice husk, and other types of biomass in a very effective way. In category 2, we have burners that mix the axial and radial primary air inside the burner in a chamber located toward the burner tip. In this category, we have manufacturers such as FL Smith and JetFlex burner with capacities from 8 to 200 megawatts and the use of different fuels among coal, petroleum, coke, anthracite, heavy oil, diesel oil, and also biomass such as fluff, papers, plastics, wood chips, dry fluff, etc. And the last category are burners with adjustable axle and rudder primary jets in a single channel now, with or without swirl. Swirl adjustment is a very a characteristic that can offer effective combustion, and different choices of according to manufacturer exist in order how to succeed this swirl and the relation of primary air with fuel and secondary air. So in order to sum up, primary techniques such as low NOx burners are in principle applicable to most types of fuels used by energy-intensive industries such as cement, steel, chemicals, promoting energy efficiency and contributing to the reduction of CO2 emissions through the use of green alternative fuels such as biomass. However, some primary techniques used in other industries cannot be used fully in the magnesia industry, such as low NOx burners, because the magnesia industry has the characteristic that its products are produced in high temperatures. So this type of burner operates, the low NOx burner usually operates until 1060 Celsius. But in magnesia industry, when you produce DBM, you need temperatures above 2000. So in Bamboo project, a novel and versatile low NOx burner was implemented by GM in order to lower the respective emissions for temperatures up to 1600, but also be able to produce high enough temperature for the production of DBM. So the new modified burner of GM that in the afternoon session Haris Giannulakis will present is able to combust mixtures of pulverized biomass and paid coke, but having adjustable swirl to operate as LMB for the temperatures up to 1600 in order to produce CCM, and this burner can also be changed to normal operation mode if the company wants to produce DBM production and so needs temperatures very high, above 2000. That's all for me. Thank you very much for your attention.
Nikos, for your presentation. So now is the turn for the attendees to ask your questions if you have. So in fact, we had one question. Okay. We had one question from Mr. Prajapati to Turboden concerning the ORC. So the question was if we can use biogas, so gas generated from food waste, as heat source for the organic ranking cycle. And if the biogas will have sufficient calorific value to evaporate the organic fluid. Okay, so Tommaso, please, if you can answer this question from Mr. Prajapati.
Yes, so basically what we will have to characterize in this case is the calorific value of the biogas available, and also the quantity, so the flow rate of biogas that is available, to understand how much thermal power there is in this fuel, and therefore understand what is the possible ORC size that can be developed. Concerning the calorific value, I guess that there should not be no problem, meaning that let's say we can work in certain applications like flare gas, where other technology cannot work because of low calorific value. But let's say without knowing the specific characteristics of this biogas, it is hard to say yes or no. So this is my answer. Also, it is a matter of understanding if there could be other, let's say, technology that could be exploited also, because we know that, for example, reciprocating engines can work on biogas depending on the characteristics of the biogas. So the first thing to understand is what is the composition and therefore the calorific value of the biogas, and then let's say select the most proper technology, and of course ORC could be one of these.
Okay. So thank you very much. Any other question? We have no more questions in the chat, but maybe any attendee have any doubt? Of course, you can write to us. We will share with you both the presentation, but also our contacts, so that you can directly contact us, as my colleague Luis said, concerning the CFD simulations. Okay, so if we don't have any further question, we can close this morning session now. Sorry for the delay ending this session, but we think it was a very fruitful, very interesting session, and thank you to all our speakers for those fruitful presentations. So we welcome you to this afternoon, where we will see how these presented technologies can be applied in real environment, in the industry, in the intensive industry industries. So thank you all, and let's see you this afternoon at 2.
Thank you very much.
Thank you.
Thank you.
See you.
Thank you.
Bye.
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 See you later.
Bye.